Welcome back. Today we will cover chapter 5 and chapter 6. In our previous session, we focused on the how many of text counting occurrences through bag of words and TF-IDF approach. While effective, those methods are purely syntactical. They ignore the neighborhood of a word, which is where the true meaning resides. As the linguist John Rupert Filth famously said, a word is known by the company it keeps. Today, we will explore from simple syntax to semantic embeddings. We will map the progression of NLP algorithms from word to vec, which captures word level context. Then we will explore fast text, character level morphology, and eventually to macro level representation like dark to vec, and we will also explore universal sentence encoder. This is the journey of turning human intent into mathematically computable spaces. As its core, word embedding is a learned representation where each word exists as a vector in an n dimensional space. The magic of this approach is that it allows us to compute analogies through simple vector algebra. For example, if we take the vector for man, subtract king, and add queen, the result is mathematically closest to woman. This works for geographic relationships too, like France plus Rome minus Italy will be equal to Paris. The model is not just memorizing definitions, in fact, it is capturing relational geography. Whether it is a gender status or a capital cities, these embeddings encapsulate dynamics that remain identical across different concepts, allowing machines to understand synonyms and antonyms with the high precision. The word to vec achieve these results using a simple neural network architecture with two primary methods. One is called skipgram, and continuous bag of words CBOW. In skipgram, we provide a target word and ask the model to predict the surrounding context words. In a continuous bag of words CBOW, we do the opposite. We provide the context and predict the missing target word. To make this efficient on massive datasets, we use optimization that is called subsampling, which basically removes uninformative words like the from training, and negative sampling, where the model only updates a small fraction of weights for unrelated words. This ensures the model learns quickly without being overwhelmed by the sheer size of the vocabulary. When we instantiate a word to vec model, we can configure several parameters. We define the size, typically between 50 to 300 dimensions, to capture varied data relationships. We also set a minimum count to filter out rare words that don't provide enough context. We trained we can measure how far one document is from another using the word movers distance technique, WMD. Unlike simple cosine similarity, this word movers distance technique calculates the minimum travel distance for the words of one document to reach the words of another in semantic space. For example, even if Obama speaks to the media and President greets the press share no identical words, but by using this word movers distance technique, it recognizes their semantic proximity and assigns them a small distance. Moving beyond individual words, doc to vec allows us to represent entire paragraph as fixed length vectors. While we could simply average word embeddings, Doc2Vec does better by introducing a paragraph ID. In the paragraph vector distributed memory, which is called PVDM approach, this ID acts as a persistent memory that captures the overarching topic while predicting words. In paragraph vector DBOW distributed bag of words, the model ignores word vectors and usually uses only the paragraph vector to predict randomly sample words from the document. This is particularly powerful for tasks like document clustering or ranking resumes against a job description, where the overarching theme is more important than individual word counts. Standard word to vec has a major weakness. It cannot handle out of vocabulary words or misspellings. If the word is not in the training set, the model is lost. Fast text techniques solve this at the subatomic level by breaking word into character and grams. For the word language, it stores vector for LA, LAN, ANG and so on. The final word vector is then the summation of these constituent parts. This is a spelling correction superpower because the representation is derived from subwords, so fast text can infer the meaning of a typo mistakes, like if you want to write the word explain and you have missed the character X, then it recognizes it and and definitely it will give you as an alternative suggestion the complete word explain. It captures the internal morphology that word level models completely miss. Finally, we reach the peak of macro representations. Sentence to vec extends the fast text and CBOW architectures to the sentence level, averaging n-gram embeddings across the entire sentence to consistently outperform Doc2Vec baseline. Then we have Google's Universal Sentence Encoder, which is called USE technique. This is a pre-trained powerhouse trained on vast web corpora using advanced deep learning like transformers and deep averaging networks. This technique use USE is designed for transfer learning. You can take this robust pre-trained model and apply it to your custom dataset with the minimal fine-tuning. It represents the state of the art in fetching high accurate sentence level embeddings at scale. To summarize our journey through the chapter 5 and 6, we can look at this embedding ecosystem matrix. Each algorithm serves as a specific technical superpower. Word2Vec is our foundation for semantic analogies. Fast text is our safeguard against misspellings and unseen words. Doc2Vec gives us persistent memory for variable length paragraphs. Sentence2Vec provides highly efficient average sentence representations. And finally, the Google's Universal Sentence Encoder USE offers pre-trained macro embeddings for large-scale transfer learning. Selecting the right tool depends on your data. Are you working with the individual words? Are you working with some noisy social media text or complex document? With these tools, we are ready to identify patterns and solve real-world NLP tasks.